Um, last couple of weeks as well have been super exciting. And today's session promises to be even more amazing. We have someone here today who is going to be taking on this particular session and will be giving us in-depth knowledge on what we need to understand about embeddings and vector databases. I see we do have like a good number of persons currently on the call. So welcome everyone. And if you're just joining, welcome also. We'll get started right about now. But before then, I need to give you a hint on who Kacper is. So let's see. Yep. So yes, so basically, as you can see on my screen, right, Kacper Lukawski is a software developer and data scientist at heart, and is inclined to teach others, which of course is one amazing thing why we have him here today. So everyone is going to be able to learn from him. As a senior developer advocate at Hydrant, the leading high-performance open-source vector database, he focuses on data engineering, machine learning, semantic search, agent-driven AI systems, and community building through initiatives like the LLM Camp and deep learning, deeplearning.ai courses. Kacper is also the founder of the AI Embassy Foundation, which he's using to promote AI education. So if you're new to the AI Embassy Foundation, you might want to look it up online and then learn more about what Kacper is doing using the AI Embassy Foundation. Ladies and gentlemen, that being said, put your hands together for Kacper Lukawski as he takes over and gives us an amazing one for today's session. Hello, Kacper. Over to you.
Hello, thank you. Thanks for the invitation. That's a real pleasure to be here with you today. Yeah, somebody has asked about the proper pronunciation of my name. I know, especially the last name might be pretty hard. My name is Kacper Lukawski, but overall, everything about me has been said already. I'm a senior developer advocate at Quadrant. We are building a vector database. However, I prefer the term vector search engine. We'll discuss that in a minute. I also created an AI Embassy Foundation, and I also try to blog on my personal website. So feel free to have a look at it. And without further ado, let me just go straight to the today's topic, because we meet to discuss embeddings and vector databases. And obviously, we need to start with the embeddings. I'm not sure how many of you have any experience with using embeddings in your projects. However, I believe that if you treat generative AI seriously, and if you have ever built any kind of a system that uses Gen AI to create even like a simple chatbot, then you have probably also utilized retrieval-augmented generation, which is part of the modern Gen AI stack. So let me just briefly discuss the embeddings and their role in building this kind of systems. So first of all, neural embeddings. Neural embeddings are some sort of data representations that represent input data in a fixed n-dimensional latent space. That means neural embeddings might be produced out of your text, images, audio signals, videos. I see there are some questions. Could you please maybe use chat so we can answer them, or if there is a Q&A section here. I'm not really sure if it's a Q&A section on Google Meet. But feel free to just interrupt and ask your questions whenever you feel it makes sense. But coming back to the neural embeddings, they're created by neural networks which are trained for that purposes. So these neural networks can take some sort of input data. Typically, it's just text, but it might be any different data modality you could possibly think of. And it transforms unstructured data, such as text, into structured format that has a specific number of dimensions. And this has a pretty useful property that if we have two different objects, and if we convert these objects into vectors, into vector embeddings, the similarity of those two embeddings should be really high, if those two objects are similar in some way. Obviously, there is not a single method of how to define the similarity, but generally there are some pre-trained models that you can use for that purposes. And even though there are different ways of how to calculate the similarity, cosine similarity is the most typical choice. As we probably all know, cosine function has a limited range of values it can take. It's from negative to +1, and this is actually pretty useful in many cases because it might be automatically transformed into 0 to 1, and this is like a natural indicator. There are different ways of how to calculate the distance or similarity, like Euclidean distance, but in that case it is virtually unbounded, so it may take any value, and it's really hard to say whether similarity of 20 is better than of 25 or how much better it really is. So cosine similarity is pretty useful, and this is the similarity function that we typically take. And as a result, if you take a model that can provide you with these embeddings, and if you just try to calculate the similarity, you can expect those two examples to be quite similar to each other. Like probably all of us have written a lot of emails, especially if you work in big corporates, and if you just type "hope it helps," just stop bothering, is typically what you really mean. And if you just compare the individual dimensions of both vectors at the very bottom of the slide, you could see that these individual numbers are not identical, but they are actually pretty close to each other. And that probably indicates that if we calculate the similarity of these both vectors, it should also be relatively high, just because the differences of individual dimensions are not that big. And similarly to that example, if we take another one, thanks in advance, and I'm already thanking you for doing me this favor, even though you haven't yet agreed to it, therefore we must do it. Still, the similarity is also pretty high, just because those two sentences represent the same intent of the original writer. And that's the high-level intuition. However, we are just going to dive deeply into the different types of embeddings that exist, because neural embeddings are not the only one we have. And I just want to really speak about the nuances of how these embeddings are created internally within those systems. So, as said, there are different kinds of embeddings, different kinds of vectors we use for search, because that's what ultimately these embeddings are primarily used for. And dense embeddings are the ones that I just described. Dense embeddings and neural embeddings are just used as synonyms. And if we speak about neural or dense embeddings, we typically mean the same thing. Those are the embeddings which are produced by neural networks, and typically they produce dense representations, meaning all the output dimensions are non-zero. But what exactly happens if we take a neural network and try to use it for creating the embeddings or try to train it? I'm sorry. So first of all, we have a tokenizer. The tokenizer splits the input data into tokens. And those might be just whole words, like in our example. But if you have longer words, or if you work with multilingual data, then a single word might be even divided into multiple tokens. But I think like all of us should already be familiar with the concept of a token, because we pay for tokens if we use generative AI models such as ChatGPT or Claude from Anthropic. So basically the story here is exactly the same. There is a way to divide potentially unlimited text or data into some digestible units. In this case, each token is just a single word. And what happens next is that the tokenizer has a mapping between the token and its vector representation. And this initial vector representation is just something that the model learns during its training phase. So the intuition here is that every single token has some initial representation created by the model, which is some sort of global understanding of what this particular token means. And what happens next is that we take these individual representations of each of the tokens and pass this list, this array of tokens as through the multiple layers of the transformer model. So we take those initial embeddings and transform them into a different set of embeddings, but the length of both input and output here is identically the same. So we can also say that each of these embeddings just get more and more understanding of the overall context. So it's not only about the meaning of that particular token, but it's also about the meaning of that particular token in that specific context, because we all know that the meaning of the words may vary depending on the context of the sentence or a paragraph. And it's just a way how the transformer model brings that additional context and changes the representation of each of the tokens depending on the different tokens in the input text. So there might be just multiple layers of the transformer model. The more layers you have, the more complex relationships we should be able to detect. However, if we speak about the embedding models, the complexity of them is relatively low compared to the generative models, such as LLMs. Just because here we just want to transform the text into the representation, which is like a fixed dimensional vectors, and in generative AI we just want to reconstruct the next token based on the sequence of tokens that the model has seen before. So we are solving a slightly different problem here, and the embeddings just don't need that many parameters to work pretty well. And what happens at the very end of the network is that we still have a sequence of token embeddings. This time, these embeddings are just contextualized, meaning they capture the meaning of this token in the broader context. And still, we don't want to have like a list of input token embeddings converted through the model. We just prefer to have a single vector representing the whole sentence, and that's what the pooling layer is used for. So the pooling might be as simple as taking an average of all these input tokens. That means there is some compression going on, and we cannot expect the neural encoding to just capture all the nuances of the data. It typically just captures the semantics, but not with all the possible details. So it's not like you can take a whole book and convert it into, let's say, 1,000 dimensions. That would be like a perfect compression technique. Unfortunately, this kind of compression is impossible to be achieved. So we have pooling. And at the very end, as an end user, you don't really care about that, because what you want to have is a way of transforming potentially like unlimited text into a single vector representation. I said potentially because each embedding model has a certain context window length that it can accept. And if you just pass more than this, then your question, your text that you send as an input would be just truncated. So don't even try to send whole PDFs or whole books. That's not going to work. And in the worst case, you won't even notice because maybe your embedding model, the library that you use, doesn't throw an exception when it reaches, when it gets an input longer than it can process, and just truncates the ending of the sentence or the beginning of it. So it's better to be aware of that. And those were dense embeddings. So as an output, we get fixed dimensional vector with non-zero values everywhere. But there are also sparse embeddings, and those were actually pretty popular in the past. They still matter, and they are supposed to solve a different kind of problems. Dense embeddings are created in order to represent the meaning. So no matter what words you use, the model should be able to understand the meaning of your document, and possibly that helps to find some relevant documents, even though you use completely different words. However, sparse embeddings have this property of being able to find documents based on the presence of particular keywords. And that makes a lot of sense. In many cases, if you deal with documents containing lots of identifiers, for example, from the dense embedding model perspective, it doesn't really matter. Like, those identifiers are just random sets of characters and numbers. and it cannot understand the meaning of a particular sequence because it hasn't been exposed to this identifier during this training phase. Those models are typically just general purpose, and they quite well understand the natural language, but not a very specific niche domain that you might be working on. And sparse embeddings are the way to go if you really deal with this kind of problems. So what's the difference? Here, in the sparse embedding model, we also have a tokenizer that divides the input text into pieces. There might be also some normalization happening. For example, jumps could be converted into jump, so we can have just a single root form of each word. So jump, jumps, jumping will be all converted into the same representation, which makes a lot of sense. We are not considering grammar here that much, but we mostly care about the meaning. However, that really depends on the model. And these tokens are just fed into the sparse embedding model that calculates some values for each of the tokens. There might be also some additional processing done, like removal of the stop words. That happened in that example, like D was removed because D doesn't bring any value to the meaning of the sentence. So it was just removed. And as a result, you can only see hopefully meaningful words. And each of these words has its own position in that vector. So in that case, the vectors produced by sparse embedding models are just way higher dimensional than the ones produced by the dense embeddings, just because the length of this vector is just equal to the length of the dictionary you have. So all the words that you support have their own corresponding dimension in the output vector. So that's how sparse embedding models differ from the dense embeddings. Practically, if you implement that, like majority, I would say more than 95, sometimes even 99% of the dimensions will be just zero. So we implement that differently, and we only pass the non-zero values, so the corresponding indices in that long vector and the corresponding values of these indices. So that's how sparse embedding models are different. And if you worked in search or in data science for a while, you probably know methods such as back of words, TF-IDF, BM25, and those methods are actually sparse embeddings as well, even though they have nothing to do with AI or ML models. There is no neural network that produces these representations. They still produce sparse embeddings, and we were using these techniques for ages. If you have ever implemented anything in, for example, Elasticsearch, there is an inverted index that uses BM25, and ultimately those are also some sort of vectors. However, there are also some additional techniques nowadays that incorporates the use of neural networks into sparse embeddings. So the main problem of the sparse embeddings, these old ones that we knew, was that they only focus on the presence of particular keywords. However, in many cases, we also want to cover the synonyms of these keywords too. And that can be done just with TF-IDF or BM25. Those methods just do not understand the meaning of the words. They can just produce the representations based on the keywords. However, if we apply neural networks to that process, they can perform something which is known like term expansion. So in that case, we had a quick Fox. So quick is a synonym to rapid, and this kind of network can also produce a list of synonyms and assign non-zero values to those synonyms as well. That makes a lot of sense. However, sparse embedding models based on neural networks are also relatively heavy compared to the dense embeddings, and that really depends on a particular problem you're trying to solve. However, they do exist, and it's better to know. Again, as an end user, you don't care as much about the inner workings of these models, but probably just want to have a system that will produce these sparse embedding representations based on the data you pass to it. There are various ways of how to use sparse embeddings, and it's good to know that dense embeddings are just supposed to cover the semantics, while sparse embeddings are better suited for keyword matching or exact matching, and they are also known as lexical search. And we are not done yet. Actually, there are dense embeddings, there are sparse embeddings, but there are also multi-vector embeddings nowadays. So instead of producing a single vector representation for the whole document or query, you can also produce a set of vectors. For example, assign a separate vector to each of the input token in the sequence. So it's no longer a single vector representing a whole document, but each of the tokens in the document and the query may have its own token. And here it just changes the way we calculate the similarity, because we need to take care of the similarity between each of the pairs. So each of the query token is compared to each of the document tokens. So as you can see, this approach might be just slightly slower, but there are models such as Colbert, which are called late interaction models, that use this kind of multi-vector representations. Those single token embeddings are also dense. And the difference here is that this kind of representation should be able to capture all the nuances in the data, because they also have this individual representations, not a pooled version, which is just an average of all the tokens. So it actually makes a lot of sense if you really work on a problem that requires this high level of understanding of the data. And there are some problems with scaling multi-vector search, so it's actually not advised to start with multi-vectors retrieval from the very beginning. It's better to just gradually test different methods and use the simplest way possible. And both dense and sparse embeddings are just pretty simple to implement. And this is like a more complex way, however, typically better in terms of the quality. And we've just discussed all the possible flavors of the vector embeddings. However, you may still wonder, why do you actually need a vector database? And the vector database is a pretty popular tool nowadays. However, when I joined Quadrant in 2022, nobody was even speaking about vector databases. That was a completely different word. Like, we were rather positioning ourselves as a different paradigm of search, because that's ultimately what vector databases do. And it is all based on this different kinds of embeddings, starting from the dense embeddings. So vector databases solve actually a pretty unique problem, and many tools started to incorporate this technique into their systems. However, vector databases are just built ground up to support vector search in an efficient way. So we already discussed that, but if we have two different embeddings which are close to each other, then that indicates that those two objects represented by those embeddings are also similar in some way. However, the main problem here is that we need to find the k nearest neighbors by calculating the distances of the query vector to all the document vectors, all the document embeddings. And it doesn't scale at all if you think about it. Because imagine you have potentially millions of documents in your system, and if you would like to find the k nearest neighbors for each of the queries, just in a naive way, you would need to calculate million of distances for each queries, and that means it's not going to take like a few milliseconds, but it will take at least a few seconds or maybe even a few minutes to do that, even if you run this search in parallel. And especially if you have multiple concurrent users trying to access the same collection, access the same data set and search over it, then that means that you would need to calculate millions of distances over and over again. And yeah, apparently that's also a blocker to apply k nearest neighbors without a specialized data structure. So Quadrant and actually all the vector databases out there, they perform a process which is called approximate nearest neighbor search. And approximate means it won't always produce the same outputs as pure k nearest neighbors. However, the search precision is typically higher than 95 or 99, even depending on how you set it up. So that means we are sacrificing the search precision a little bit for the sake of speed and performance. And all the vector databases use some sort of data structures to speed this process up. Quadrant uses HNSW, which is one of the most promising algorithms for that. And this data structure is based on a multi-level graph, which is supposed to just provide a faster way of finding the closest matches in that vector space. In other words, if you want to do vector search effectively, you have a set of documents and you want to send some queries and find the most relevant ones. Approximate nearest neighbors is your way to go if you really want to build a scalable system. And let me just briefly speak about how we do that. So we have this approximate nearest neighbors algorithm called HNSW that solves the problems of KNN, which is actually one of the most basic machine learning algorithms, if you think about it. KNN, K nearest neighbors, is something that is quite a common technique. However, it is known for being hard to scale, and that's something that vector databases solve pretty well. So HNSW, the algorithm that we have, mitigates all the problems of the KNN. That means like brute force approach, requiring to calculate all the distances to all the points for all the queries that you send, as it only can be done for relatively small data sets. And HNSW just builds a multi-layer graph. So in the first layer of that graph, you have a very sparse network. So it's just few of the candidates of the whole data set, which are connected to each other based on the similarity. So if 2 points in that first layer are similar to each other, there should be like an edge connecting those 2 points. And there are just multiple layers of that graph. So when you start to search, you're just trying to find the closest neighbors in that first layer, and then by using interconnections between the different layers, you are just going to the more dense layer, and here continue your search from the previously found candidates. So it actually helps to reduce the scope of search, because we are not looking in the subsets of the data that won't be relevant either way. And by using that approach and by gradually getting to lower layers of this HNSW graph, we are able to restrict the scope of search quite well. So this is a graph-based structure. You don't really need to know that if you are just a vector database user. However, it's good to know HNSW scales really well, just because there are some other tools claiming to use different techniques, and these techniques might not be as powerful as HNSW, which is just like a state-of-the-art and de facto the standard way to approximate the nearest neighbor search. And that brings the topic of semantic search. So we know at this point, hopefully, that there are different kinds of embeddings. Vector databases just makes this process of retrieving the closest points in that vector space efficient. And semantic search is actually a technique that is used to build retrieval based on the embeddings. So semantic search involves 2 different processes. So the first process is the data ingestion that takes our documents, processes them through the encoder, and puts into a vector database. And here, if you have ever built retrieval augmented generation, you probably already know that. But when I speak about the documents, I don't necessarily mean like your whole PDFs or whole books or even whole pages of these documents, but I rather mean paragraphs, sentences, some smaller chunks, but yet still meaningful chunks of the documents that you extracted from it. So there is actually an additional process which is not covered by the vector databases themselves, but that's an additional effort that you need to do in order to use semantic search effectively. So when I speak about the documents here, I mostly speak about these chunks that do not exceed the context window of the selected embedding model. So those documents are just encoded into vectors and then stored in a vector database along with the original content that was used to create them. So we not only need to have these embeddings, but typically we also need to have the text that was used to generate the embedding, or maybe if you work with images, there might be like an URL of an image that was converted into that particular embedding. And this is the ingestion pipeline, which is typically a bottleneck of all the systems. Like processing potentially millions or billions of documents will definitely take some time. So it's better for you to just test different embedding models that exist and see which one of them just works best in a very specific case that you are trying to solve. Like if you use libraries such as LangChain or Llama Index, there might be some default models like OpenAI embeddings, which are quite okay if you work with English data. However, the support for non-English text is just not documented. Some people report that they work pretty okay with German or French. However, it's not tested, and this model was just not designed to support them in the first place. And if you work with multilingual data, you just need to focus on choosing the right model from the very beginning, because it's really hard to switch to a different embedding model once you just encode all the documents. There is no way to just recalculate these embeddings quickly. You just need to repeat the whole ingestion process again, which might be done. However, it's just better to start with a good embedding model from the very beginning. Having said that, let's just come back to the second process, which is just a lightweight, since you use vector databases. Because here, when we receive a query, we need to pass the query through the same URL encoder and use the output query embedding to find the best matches in a particular correction. This is typically done with cosine similarity, and that gives us a list of the candidates that are possibly the best matches for that particular query. So this architecture is called by-encoder because we use the same model twice. So this is the whole process of finding the most relevant documents. As you can see, here we are just creating a single embedding, so it doesn't make this process too complicated. Like this is usually taking not more than just a few hundred milliseconds. And still, since you need to use the same model as you used in the previous step when you were ingesting your data, it's better to just consider it and for a while and choose the best model that you can possibly find, or the best model in terms of its cost and efficiency in a very specific problem you are solving. And this is also one of the key components if you work with generative AI. Semantic search is quite typically the default way of how to bring your private data into the LLMs, because obviously none of the LLMs, the public ones we can use, was trained on the data that belongs to your organization or maybe to yourself. It's because you might be having like some private knowledge base that you would like to utilize with the LLMs. However, you are not really able to expose this database into the LLM training data sets. Obviously, for many reasons, we shouldn't be doing that. Also, that's one of the ways of how to reduce the risk of hallucinations, because it slightly changes the way of how we interact with the LLMs. So this is the most naive approach of how we can work with the LLMs. So there is like a user, they create a prompt, and this prompt is just sent directly to the LLM. So there are multiple risks here, like the LLM doesn't know anything about our company, our data that we possess, neither about the user who created that particular prompt. So it's just like sending a free from text to the LLM that can produce some output. However, we cannot expect this output to be accurate, and there is high risk of hallucinations here, especially if our question or our prompt is not like related to general knowledge, but it's more like very specific focus on our domain and our company, for example. So retrieval augmented generation is changing that paradigm, because here, instead of asking the LLM directly, we use this prompt sent by the user as if it was a query, and we encode this prompt through the same embedding model, and this embedding that it produces helps us to find some relevant documents in our knowledge base. So then, instead of sending the prompt directly to the LLM, we send the original prompt along with the retrieved documents, and we ask the LLM to produce its output based only on the documents we provided. So that changes the way we use the LLMs a lot, because instead of relying on their knowledge that is somehow encoded inside of their parameters, we rely on the language capabilities of the large language models and use their summarization or extraction capabilities to find the relevant information in the provided context only. So we build some sort of a meta prompt. So it would typically look like, in the most basic form, if I ask this question, like, how can I create quadrant connection? The prompt that we will build will be answer the question using the provided context, then we will pass the context, and at the very end, we will pass the original question. Probably there will be also some additional restrictions, like if there is no response in the provided context, please just admit you don't know the answer, because otherwise the model would typically try to make up the answer and hallucinate about the proper response. And that's why semantic search is a pretty important component in that setup. If we interact with large language models, then we typically expect them to be able to handle this natural language-like conversations, like with a chatbot. And semantic search is just well known for its capabilities to encode the intents, the semantics of the data. So we can still use natural language-like interactions. We don't need to produce our prompts as if they were just Google search queries, but we are just communicating with the system as if we are communicating with a real human being. So that's how retrieval augmented generation works in a nutshell. And there are also some other use cases of the embedding models or of the semantic search, which are surprisingly ignored. And I don't really understand that, because there are still powerful methods that can solve different problems that you could possibly have. So for example, approximate nearest neighbors or just nearest neighbors search, semantic search, might be also used to perform classification. Imagine you have embeddings of dogs and cats in your vector database collection, and there is a new image, and you know there will be a cat or a dog on that particular image, but you don't know what exactly. In that case, you could perform semantic search, take, let's say, 100 nearest neighbors to that particular image, and then by applying a voting procedure, you can just select the most common label across these 100 examples. So it doesn't only give you like a prediction, this is a dog, this is a cat, but it also estimates the probability of that particular image belonging to a certain class. So because the 90 out of 100 closest neighbors of that particular image were cats, I assume the probability of this image being a cat is 90%. So that might be done. You can use semantic search for classification, but also for regression. Regression is a slightly different problem from classification, because in regression, we don't want to predict a class, but a numerical value, which might be like an average, let's say, an average number of purchases of a particular product based on some attributes. So here, we don't really look for a class name, but instead we want to have like a numerical value. Also, if you perform semantic search and then average the value of that particular metric across the closest neighbors, you could also estimate that value. That not necessarily need to be an average, that might be a median value or maybe some sort of a range. Still, that might be solved with semantic search as well. And also, since we have this cosine similarity or any different similarity measure, we can also potentially solve the problem of anomaly detection. Imagine you build a retrieval augmented generation system for a very specific company, and this company operates in a very specific industry. So the expectation is that all the queries that this chatbot can accept and process should be coming from a very specific set of possible questions. So obviously people can express themselves differently, so there is no way you can cache all the queries and only expect the system to support these queries that you have seen before. However, the overall semantics of the queries should be just similar to each other. So if you see there is a new query coming in, and the similarity of that query is relatively low if you compare the similarity to the past queries you had, then you can safely assume that maybe putting human in the loop in that specific case makes a lot of sense, just because there is somebody trying to ask a non-standard question. Still, this is a pretty useful system because you are able to automate majority, let's say 80% of the cases, and for the missing 20%, you will be just handling them with humans in the loop. Still, you reduce the amount of human labor, and you can focus on this 20 non-standard percent, like 20% of the non-standard examples that people can possibly use. And that makes a lot of sense if you work with large language models, because if you expose a chatbot that uses an LLM under the hood, some people may just try to use it for their own purposes, and for example, use your chatbot to produce some structured output or to parse the data they pass to your chatbot. That might be done, and if you pay for the tokens, each of the users of your chatbots, like, they are just producing some cost because you just need to pay for the tokens used in a particular model to the LLM provider you selected. And in that case, it just makes a lot of sense to have this sort of guardrails. So when you detect a non-standard usage of the chatbot, you can just react quickly, and maybe at some point you decide this is a pretty valid use case. Let's just add this query to the list of the queries we expect to support. But if you see like somebody is passing you a huge JSON and trying to modify your system prompt in a way that it will just ignore all the instructions you gave to it, but it will just like process this huge JSON and maybe produce a different format out of it, then you are pretty sure that the similarity of that request will be just slightly different from the other requests you have. And last but not least, recommendations. Imagine you have a Netflix-like system when you have some movies or some items a particular person has interacted with in the past. Each of these items, a movie, product in your e-commerce system, might be expressed as a vector based on its content somehow. In case of a movie, that might be just a description of the movie. Maybe you have a pretty good model that can work on the video directly. Doesn't really matter. However, you can use even multiple vectors to produce the recommendations, and there might be positive and negative examples. So your semantic search will prefer to be close to the positive examples and far away from the negative ones. That makes a lot of sense. And setting up this recommendation system might be done even if you have just a single collection. You don't really need to use different kind of models to create your embeddings. You can have a single collection that will be performing all of this. So you will have semantic search, you will have classification, regression, anomaly detection, and recommendation systems using the same embeddings. So multiple problems might be solved with the same exact pipeline. And Quadrant is one of the leading vector databases out there. I prefer the term of vector search engine. Like the expectations from the database are slightly different than the ones that we typically have from the search engines. Like when I speak about the databases, you probably mean something like Postgres, so a relational database that has all these ACID principles in mind. However, search engines are slightly different systems, slightly different in a way that they're built in order to support search effectively. So there is no atomicity typically. So if you perform multiple operations, there is no, like, we do not have a concept of a transaction that is so typical for relational databases. And relational databases are built in order to store and process transactional data, like all the purchases. Imagine you have an e-commerce store and you have the last piece of a particular item. So a purchase, a simple transaction looks like following: like somebody orders a specific item, and at the same time we are just reducing the stock because like the last item has been just sold. But in case of search engines, there is not such a mechanism. Like you cannot expect to execute those two operations, like making a purchase and reducing the stock at the same time. Like we do not guarantee that. Search engines are built for totally different cases, and we have totally different data structures to make that process efficient. Like in relational databases, there is also a concept of indexes. However, these indexes are supposed to perform exact match. For that, we use hash functions, for example, or range search when we use B trees or any additional data structures that make that process efficient. With search engines, the requirements are slightly different. So I'd prefer the term vector search engine. However, the vector databases have been already adopted, which might be just a bit misleading. So let me just go straight to the Quadrant APIs, because that's something I would definitely need if you decide to work with Quadrant. And obviously, you can ingest your data. There is an ingest endpoint, so this is pretty obvious. But the most important thing is how you can query your data. And there was a search API. It still exists, and the search API can take a vector. You can also determine the number of elements you expect to have. So this is the limit parameter, and there might be also a filter. It's completely optional, but the filter can help you to filter out these points that fulfill a particular criteria. So, for example, if you are looking for a restaurant, which is similar to the one that you liked, you can express your preferences as a text and then convert that into a vector, and then try to look up for some similar restaurants using that vector. So that's okay. However, if you live in a very specific region of the world, then you don't really need to see like all the other restaurants around the globe that you would possibly like. You really need to get the restaurant that you can easily get to in a reasonable amount of time. So if you are in London, then applying this filter on the payload makes a lot of sense too, because you only want to see these restaurants which are close to you and that fulfills your tastes criteria. And one important thing here, there is also a concept of a payload in Quadrant. So you not only store a vector, but you can also store it's optional, but well, you typically want to store some additional metadata information, and we can accept any arbitrary JSON object. So this object may have some nested keys, some nested fields. Doesn't really matter. Quadrant is quite flexible here. And the main thing about payload is that payloads might be used to perform this additional filtering. So you can express this additional criteria that won't be captured by the vectors themselves. Like imagine an e-commerce example again. If you have vectors created out of the product descriptions, these descriptions will typically capture the visual look of the product you are selling. If we speak about clothes, maybe some color information to maybe like an occasion that you could possibly use that particular piece of clothes for. So this kind of meaning of this kind of description of the product itself. However, it will never capture the price. Price is actually dynamic, so the price today might be different to the price yesterday, and the manufacturer as well, and many other factors. So if you encode, for example, images, like in that example, the embedding will probably capture the look of the product, not the specific traits it has. And payload indexes are actually built to support the non-vector criteria as well. So if you want to find a shirt that was produced by a particular manufacturer which is of a particular color, fabric, or under a specific price threshold, then payload fields should be used for that. You can store this additional metadata information along with your vectors. And if you want to filter based on a particular field, then you should also create a payload index, which are just secondary indexes in Quadrant that can make that process efficient. Okay, this was it about the payload indexes. Just wanted to highlight there's such a feature. There is also a scroll API, which is, I have to say, like not all the vector databases that exist support that feature, which is slightly unusual to me. However, Scroll API that we have is supposed to handle the case where you don't want to search using vectors, but you only want to find some products based on the filter, or just export all of them, because you are ultimately the owner of all the points in Quadrant. So what would we block you from doing that? So this is like getting all the points from the collection. There is also a recommendation API where you can pass multiple positive and negative examples. So as I said, if you work for another Netflix like platform, you could possibly build a recommendation engine based on the past interactions of a particular person, positive and negative interactions as well. And Discovery API, last but not least, here it's slightly unique feature of Quadrant. You can express search in a different way. So you have a target vector, which is like a query vector, and you can also say that I want to be closer to that point than to the other point. So as you can see in the context, I'm just passing 2 pairs of points. So I want to be closer to the point with ID of 100 and far away from 718. And similarly here closer to 200 and farther away from 300, which are just point identifiers. You can also pass a vector here as well. So what it does ultimately is that we divide this vector space into sub-regions, and we just want to be closer to the positive points and further away from the negative ones. So this is slightly similar to the recommendations, because we can have multiple examples here, and that makes a lot of sense if you not necessarily know what you are looking for, but you just know that you like or dislike particular items, and you have just vague understanding of what your expectations are. So this is an exploratory search, and as a result, you can just prefer some specific sub areas of that vector space. And this is just something truly unique that Quadrant provides for the exploratory research, because you can just iteratively look for some points that fulfill your criteria. Just kind of cool, and I feel this is an underlooked feature of Quadrant. Not that many people use our Discovery API, which I find really surprising, because this is really useful when you have this kind of signals already. And I mentioned all of this APIs. However, currently we suggest you to switch to the new Universal Query API. And this Universal Query API is actually getting all the old APIs that I mentioned, like recommendations, search, and context, and Discovery API, and integrates them into a single endpoint. So we can build even multi-stage retrieval pipelines if you wish. For example, there are different ways of how you can embed your data, like sparse, dense, multi-vector representation, but there are also different models belonging to each of these categories. Like you might be using multiple sparse or dense embedding models in the same collection. Like you can have several representations of the same point in a single collection and use all of them if you want to. And in that case, you might end up with such a list of representations. So you may have a dense embedding, you might have a dense embedding, but using integers to just compress the data and reduce the memory usage. You may have a sparse representation as well, maybe some Matryoshka embeddings that I haven't mentioned yet, or late interaction, which will be just a multi-vector representation. So each of the points will get multiple representations at the same time. And in the Universal Query API, you can build a multi-stage retrieval pipelines in which you will be using the faster models at the very beginning of the retrieval, like here, small byte vector, the inner retrieval method will be used to restrict the scope of search to just 1,000 candidates. Then full dense vectors will be used to re-rank these candidates into a list of 100 best matches, and eventually multi-vector search will get the top 10 results. So that's ultimately an idea behind the Universal Query API, that you can combine different ways of how to search in a single API call. And this Universal Query API covers not only search, but also recommendations and discovery search too. And that means that if you have both dense and sparse embeddings, and you would like to use both of these methods in parallel and hopefully get the best out of both worlds, you can do that with our Universal Query API, because you can also use the built-in fusion mechanisms such as reciprocal ranked fusion. So you can combine the results coming from different search methods and produce just a single set of results. So no matter if your users will prefer to use keywords or just type natural language like queries, you can just support them using the same search pipeline thanks to the Universal Query API. And Fusion is just one of the ways of how to combine this potentially incompatible search methods. And more complex scenarios would require you to use re-ranking. And re-ranking is just a more sophisticated technique for taking results from different methods and merging them together to create a final list of results. And re-ranking is typically based on a model that would be just too heavy to run on all the documents we have in a collection. Coming back to this example of millions of documents. So we can't run a model on all the documents at once, and some of the existing models just require to do that. So you pass all the documents and all the queries, and that won't scale if you have millions of documents. However, if we restrict the set of candidates to consider, they will be just efficient enough to choose the best matches, and this kind of models will typically be more accurate than just sparse or just dense vectors. For example, these late interaction models using multi-vector representations are known to be quite good as re-rankers, and they usually achieve higher precision, but they are not as fast as single vector search or sparse methods. So the typical approach is that you extract some candidates using sparse and dense, maybe multiple dense and multiple sparse models, and then pass them all to the re-ranker so it can just try to detect the best matches, because that's what it's good at. And yeah, that's how you can build even very sophisticated search pipelines. And Quadrant Universal Query API actually provides a way of building that even in a single API call. And when it comes to vector search and vector embeddings, there are some typical problems that you will be struggling with when you really scale your system up. For example, imagine you have a million of embeddings, like a million of documents. So that means a million of embeddings created, and each of these embeddings have just around 1,500 dimensions. This translates to 6 kilobytes of memory per a single vector. And if you just multiply that by a million, that means you need to have 6 million kilobytes, which is 6 gigabytes of memory, to store just this million embeddings in your memory. And you typically need to store all the embeddings in your memory because you need fast access to them. You never know which embeddings you would need to calculate the similarity for. So that's also why vector search is known to be memory-intensive task. And as usual, it's really hard to build a system that will be fast, accurate, and would require low RAM. So if you build such a system, you typically need to choose just two of these characteristics and build for that purposes. Like your system might be both fast and accurate, but it will probably require lots of memory to run, or it may be fast and require low RAM, but it won't be that accurate. And last but not least, it might be just using low RAM and it will be accurate, but won't be that fast anymore. So if you want to achieve the latter one, then you probably want to have a look at the memory mapped files, so you can store all the data, vectors, payloads, and the graph itself on disk. However, that won't be that efficient. Still, I know some users that were just satisfied with slower search for the sake of it being accurate enough, and they don't really need to have like an instant response from a system. They can accept waiting for a few seconds to get the response instead, since it's not like a real-time system. So in that case, you can run Quadrant on a very low-end machine and still work with it, as long as you accept this slower performance. And yeah, so that's one of the optimizations that we have if you're really on a budget and don't want to spin up a huge cluster in terms of its memory. The other one is pretty interesting, because it turns out that dense embeddings, at least, if they're represented as floats, as floating point numbers, a single float takes 4 bytes of memory. 32 bytes of memory, and an integer can take just 8 bytes. So that means if we are able to compress this 32 bits into 8 bits, we can save up to 4 times on memory. And surprisingly, many of the existing embedding models work still fine if you just do the scalar quantization and convert 32-bit floats into 8-bit integers. And Quadrant can actually do it on your own. If you have an existing collection and if you decide to reduce this memory usage, you can just enable scalar quantization, and then nothing changes from the user perspective, because search will be still accepting your original vectors, but internally Quadrant will just compress all of the existing vectors and build its own structure based on this compressed representations, while it will also keep the original vectors on disk. So so this is actually a pretty simple technique that can reduce the use of memory significantly, because you will just use like 25% of the original memory you would need to store these vectors. However, there are also techniques that push that to the limits. And for example, binary quantization. Binary quantization is just another technique that converts 32 bits of information into a single bit. It is as simple as converting values lower or equal to 0 to 0 and higher to 1. And it turns out that it can speed up the process of search by up to 40 times and reduce the memory usage up to 32 times. So it's generally a pretty great achievement. Still, it proves to work better for high-dimensional vectors, not all the vectors that exist, and it's better to just test it thoroughly on your selected embedding model before enabling that feature on a Quadrant collection. Still, it's a reversible operation, so even if you do your experiments, you don't really need to binarize all your vectors on your own. You just enable that option on a collection or vector level, and then all your vectors inside of Quadrant will be just binarized, and you will search on your collection in the same way like you would do without the binary quantization enabled. So so this is it when it comes to quantization. There's also product quantization, but I rarely recommend using it. If we just compare it by speed, binary quantization might be up to 35 times faster, reduce the memory usage by up to 32 times. And product quantization might reduce the memory usage by even up to 64 times. However, it comes with a typically it comes down with some bottlenecks on the ingestion pipeline, because product quantization changes slightly the way we index your vectors, and it's just not advised to use it in many cases, because you can achieve a similar speed up with binary, like even better speed up with binary quantization, and 32 times is typically enough. Still, that exists. It's not that popular, however. And I just encourage you to have a look at the articles we have about the binary scalar and scalar quantizations and how to serve quadrants on limited resources when you have some constraints on the budget. You can use like customer grade setup, and that should still work pretty fine. And this is it regarding the optimizations. However, Quadrant, even though it's an open source vector search engine, we also have our commercial offering, which is our cloud. And there are different flavors of our cloud. So let me just dive into that a little bit better. Our managed cloud is probably the easiest way to start using Quadrant. If you are not familiar with it already, you can create a free tier cluster. There is no need to pass your credit card details at all, and you will get a cluster with 1 GB of memory for free. And this is typically enough to store even hundreds of thousands of vectors. So for many cases, that should be just enough. And you can easily scale it up on demand. But there is also a pretty interesting setup, which is called hybrid cloud, that we introduced a couple of months ago, probably even a year or so, which is called hybrid cloud. So if you work in an environment where you can't really send your data into a managed cloud solution to a cloud provider, like a public cloud provider, there is also a way that you can bring your own Kubernetes cluster, and this will connect your Kubernetes cluster to our managed cloud. So Quadrant will be running on your infrastructure, completely on your premises, but you will still get the chance to control it with the Quadrant Cloud UI. So this is pretty convenient for enterprises or big companies that can't really send all the data into cloud providers such as AWS or GCP or Azure. In that case, if you have a Kubernetes infrastructure, this is a pretty interesting way of how to set up Quadrant, so you can manage that with an ease of the managed cloud UI, but still control all the resources and pay just for the resources you use, host it whenever you want. And we also support features such as lower-based access control. So for example, if you have a collection and you just want to restrict the who can access a particular collection, or maybe even a particular row, you can use JWT role-based access control implementation. So JWT stands for JSON Web Tokens, and these tokens contain claims that specify with specific access permissions. So these tokens are encoded and require an API key to generate and validate. So it's not like everybody can just create these tokens, but you just need to create them and provide to different users of the system, so they can access specific parts of the data you have in your instance. So you can give global access to all the collections you have, read and write access to all of them, or maybe just restrict it to a specific collection, or even to a very specific subset of your data through payload filtering. And it's actually pretty configurable, and that's something that we believe many of the enterprises need. So you can also like set a specific expiration date. So this particular token will be just valid for like 30 days, and then it will disappear. So I think this is kind of interesting if you build a real production grade system, because typically you just don't want to expose all the data to all the possible users of your search engine. You just need this kind of restrictions. So vector databases are also production grade systems already. And you also have a pretty interesting cloud API. So if you just want to spin up new instances with like programmatically, you can also use our cloud API for that. So you can spin up AWS Quadrant instance using an API call, or set up different cluster resources like CPU and memory and different node configurations based on the API we provide. Generally manage the API keys if you prefer to do it programmatically, not from the UI. So just wanted to mention all these enterprise grade features too, because I don't really know like who exactly is watching our session today, but apparently no matter if you just started building generative AI applications, or if you have lots of experience in building such systems and you just want to scale it up and you incorporate semantic search into an existing application, maybe you build some completely new applications, vector databases, Quadrant is ready for even this kind of loads by providing all the possible optimizations in the world of vector search and all these enterprise-grade features, so you can build a reliable system compliant with all the possible law restriction around the globe. And that would be it from my side today. I'm really happy that you decided to join us for this session. If you have any questions, I'm happy to answer them right now, but please feel free to just reach me out directly, either using my LinkedIn profile or maybe just send me a message on Twitter if you prefer. I'm just happy to discuss whatever use case for semantic vector search you can possibly have. Thank you very much.
All right, awesome. Thank you very much, Kacper, for that amazing one. So this was a very insightful session, and I believe the participants here have a whole lot that they have to take home from here. Thank you very much once again. Please do indicate if you have any questions. Do indicate if you have any questions. So you can either use the raise hand button, or you can just put your question in the chat. So kindly indicate if you have a question. All right. Hi, Martins. Please go ahead.
Yeah, good day, everyone. I don't really have experience in LLM, but I have little understanding of graph. So I want to ask this question: why he was talking about the first type of embedding, which is the dense embedding.
Embeddings.
Yeah, you made mention of stacked layers, and I was picturing stacked layers like similar layers of vectors, more like a vector basis, right? So I want to ask, is there any way you do the grouping for your for the vector database? Maybe introduces something like a vector basis, or the grouping of the vector data is just you use graph edge and node to know the meaning, like for semantics. I don't know if the question is clear.
I'm not sure if I got the question. Actually, yeah, like for me, it makes some sense to use graph to like define the meaning, if that's what you meant. It's actually there is such a technique, like you can build graph rack, for example, and like determine the meaning of the tokens or rewards based on some ontologies. So there is such a concept. Unfortunately, I don't feel like I'm an expert in that, because I'm mostly focused on semantic search and search in general, like the traditional ways. However, I feel like yeah, that's still like a valid approach. Unfortunately, I don't know like if somebody has successfully used that. Yeah, but if you have a very specific use case and you would like to discuss it, feel free to just send me a message on LinkedIn, because it's really hard to say like how to approach that. But it might be just easier if we could maybe potentially have a look at the data you would like to use for that, and that way I would be able to suggest hopefully a good way of how to approach it. Would that work for you?
Oh, thank you. I'm just trying to learn. I'm not building anything at the moment. Thank you very much.
You're welcome. I also see there is another question, like what best chunking strategy do you advise for a personalized educational system, or do you also advise any hybrid use of a couple of chunking strategies? If yes, which ones would be your top two go for? So yeah, definitely like this most naive approach to chunking, like fixed length chunks, that rarely works, to be honest. And this is just the simplest way of how to do the chunking. Like from my experience, depending on the type of the data you are working with, like in our case, we are trying to right now we are trying to improve the search experience on our documentation. That's of course built with Quadrant, but we just started to record all the queries sent to the system, or actually started a lot of time ago, but we are currently trying to combine that to improve the search experience. So we work on HTML documents. So all the documentation we have are just some sort of HTML documents. And if you read a very specific paragraph of that document, it doesn't necessarily contain all the context needed to understand it fully. So what helped in our case was that we started to collect all the headers down to this specific paragraph. So hopefully if you have your documents structured properly, if you take all the headers down to the specific paragraph, then you could possibly incorporate some more information. And if you speak about personalized educational system, that really depends on the data you have. I can't really advise you a very specific strategy. I really like the contextualized chunking introduced by Anthropic. There was a pretty interesting blog post they published. So they use LLMs to somehow summarize the whole document. LLMs are really great at it. And then the embedding of a particular chunk comes from the description of the whole document and this chunk itself. So how this chunk, what's the meaning of this chunk in the context of this document summary. So I really like this contextualized chunking. I feel like that could work in many cases, but it's pretty heavy because we use LLMs to do the chunking. So that means lots of LLM calls just to encode the data. And what's more, generally using LLMs to do the chunking, actually that's something that they are really great at. Like if your documents have a lot of context switching, then LLMs can easily detect that and hopefully divide into separate pieces. And then you can also like group pieces that are on the same topic. So that's probably something I would advise to check. So just trying to use LLMs for that. And maybe you don't even really need a very fancy LLM, but maybe you can even use like a very small language model that you can run on your laptop and test whether it can do that job well. Yeah, but my conclusion is this naive basic approach rarely work, and it's typically better to even try to build some heuristics, so some rules that will help to divide your text into chunks, or just use LLMs directly. Okay, we have another question. My question is on trade-offs. For a medical use case where recommendation is primary, which of these are best suited? Fast, low RAM, and accurate? How fast is fast compared to slow? Yeah, so basically, I would say if we work in such a domain like medicine or legal, then probably you have to build a system which is as accurate as it could possibly can be. And I would say that in that case, maybe you don't really need a system that would be like super fast. Like you can sacrifice the speed, because ultimately you are making a decision about like a possible treatment of a particular person. So I would vote for a system which is slow yet accurate. So don't need to have lots of memory, but let me think. Like, really depends. Like what I typically advise to do in such a case is that I really recommend you to focus on building the evaluation. So I don't know what are the typical use cases of a system that you build. What are the queries that you expect to see coming to the system? What are the documents, etc. However, if you can build a data set, a ground truth data set that will have queries and the documents you expect to see, the most relevant documents you expect to see, then this data set could be used for proper evaluation. And it's even better to have a well-curated data set of hundreds of examples than, I don't know, like millions of examples that you just automatically generate. And then if you evaluate the performance of a particular model, compare different models, then you can make like a informed decision of how to set it up properly. So I would say in that specific example, I would probably choose either low RAM and accurate. Definitely it has to be accurate. So there are just two options: fast and accurate, or low RAM and accurate. And depending on the budget, if I had like a very restricted budget, lots of documents, possibly billions of documents, I would go for low RAM and accurate. Or if potentially I could afford to build a system with like that would be just fast, then I would just probably build a fast and accurate. But this is just gut feeling, depending on what you build. Like if you build a chatbot, then maybe your users won't be really able to wait for, I don't know, like 30 seconds to get a response. But in many cases, they will just accept it. Okay, I see another question in the chat. Hey, Kacper, please, I have a question. You made a mention of the other use cases of vector search apart from embedding, which are classification, regression, etc. Can we perform all these other use cases on the same embedding? Yeah, that's the whole point. Actually, if you build a collection with all your embeddings, you can use it directly for search, but you can also use it for classification, regression, anomaly detection, and recommendations if you prefer to. Obviously, it's rarely the case. Like nobody builds a system that provides all of this at the same time. But yeah, you can do that. Like those are the same embeddings, and you can combine them in different ways to solve different problems without calculating like different embeddings for different purposes. I see there is another question from the audience. Somebody has just raised a hand, so feel free to. Okay, do you have any other questions then? Because okay, what are the best methods to mitigate low memory training gigabytes of data with huge architecture? I don't necessarily know what you mean by the training. Actually, the typical approach to semantic search is that you take a pre-trained model and then you just use it as it is, and maybe just fine-tune it a little bit if you see that maybe it struggles on your very specific domain. However, if you would like to train your own models, your own semantic like embedding models, then you unfortunately need to have a proper architecture, proper infrastructure. So that's where I see there might be some training required. However, the typical approach to semantic search is that you just take an existing model and apply it as it is, and there is no training required. So those models are known to be good, like general purpose models, and that's why the training is not needed. Okay, so like quantization. So quantization in if you use semantic search, quantization is not involved in the training phase. It might be, of course, but in case of vector databases, quantization is just enabled on the existing vectors. So we just modify the values of these vectors. So instead of like representing all the positions as floats, we can represent them as bits of information. So that's the whole purpose of quantization in when we speak about semantic search. But it doesn't involve like modifying the training procedure. It usually works on any pre-trained model, like without changing the training procedure of it. And I also try doing like fine tuning or even training my own embedding models. However, that unfortunately requires having like a proper infrastructure that doesn't need to be like thousands of GPUs in a cluster, because embedding models are just way easier to train compared to the LLMs. Still, some GPUs are required, at least one, so we can do that effectively. Okay, any other questions?
All right, awesome. Thank you very much, Kacper. So if there are no other questions, I think we can call it a day here. Once again, on behalf of the AI Summer of Code team, we'd like to say a very big thank you, Kacper, for taking your time out to impact these stars. We love to call them AISOC stars, right? For taking your time out to impact these stars. And we believe that definitely in the near future, they would be able to also put out all of these knowledge that they've gained from you and have it impacted to other persons as well. Thank you very much, Kacper, for your time, your knowledge. AISOC definitely says a very big thank you to you. Everyone who has been a part of this session, I believe you've all had a whole lot to digest. Yes, please follow or connect with Kacper. I think I missed out on that. Please connect with Kacper on LinkedIn and other social media platforms. There's a whole lot to learn from him, even from just his posts, right? The journey doesn't stop here. There's still more to go, and we'll keep on exploring. Thank you very much once again, Kacper. Do have a lovely rest of your day. And to the rest of the participants, I will see you all in the next session. Bye and have a good day.
Thank you. That was a great pleasure. Thank you, and have a great day.
Thank you too.